Okay. So we have ADB, CF are concurrent Sevians. Then we have AF over FB times BD over DC times CE over EA, that is equal to 1. Okay. When we look at then the angle opposite to, if we look in triangle AFC, the angle opposite to triangle in triangle AFC, I can draw here separately. So here is A, here is F, here is C. So this is angle ACF. Okay. So the trigonometric form goes sine of angle ACF over. Then for BF, the opposite is sine of angle BCF times. For BD, we have sine of angle BAD over sine of angle CAD times sine of angle CBE over sine of angle ABE, and is equal to 1. If we know the Sevas theorem, then the trigonometric form is this. So formal statement, I am not exactly now writing, but we can write it. Okay. So we can say that AP, so or otherwise I can write it as ABC be a triangle and DEF be the points on sides BC, CA and AB respectively. Then we can say that AD, BE, CF are concurrent if and only if this part sine of angle ACF upon sine of angle BCF times sine of angle BAD upon sine of angle CAD times sine of angle CBE upon sine of angle ABE is equal to 1. You can find that here we have ACF in numerator, then BAD in numerator and CBE in numerator. So you can see how alternate they are coming, and then rest are in denominator. So not necessarily in the same sequence we express this. We can write that in another sequence also, like BAD over DSC times ACF over FCB times then the rest, that CB over EBA. We can go like that. Now the question is how we are going to prove this. How to prove this? Okay. We know that in from left side, that is if they are concurrent, then this ratios product is 1, and if they are not concurrent, Yes. So when we use this, that is, we are using the what Shreyan, we are using the similarities. Okay. Or we can use sine rule, can't we? We can use the sine rule and can get something. So suppose in triangle, I say that, suppose I say triangle ABD. By sine rule, we have BD over sine of angle BAD is equal to AB over sine of angle ADB. Okay. When I use triangle ADC, I get that DC over sine of angle, what is that? CAD is equal to AC over sine of angle 180 minus ADB. We can use like this. Yes. Hmm? We know that sine of theta is sine of 180 minus theta. Sine of theta is sine of 180 minus theta. And then therefore, we get that BD as AB times sine of angle BAD upon sine of angle D. I use only D now. Moreover, DC, we get that AC times sine of angle CAD over sine of angle D, or sine D only. Okay. Because 180 minus angle ADB is the same. Similarly, we get the others. Now, we know that because of Seva's theorem, we can show AF over FB times BD over DC times and C over EA is equal to 1. Okay. That this part is well known. Or we can prove by using merely our area relations, or maybe similarities, or maybe using some 2-3 times Menelaus, and we can come at that point. Okay. So now I will rub this, because actually what is to prove that I wanted to show over there. So that is written already over there. So just I want to show that here BD is nothing but AB times sine of angle BAD, and upon this would be AC times sine of angle CAD. And sine D will get cancelled. Okay. Similarly, we can work for getting AF over FB and CE over EA by using the sine rule. And then we put in LHS, then you get that AB, AC, AC, BC, BC can be cancelled out and our desired result will come. So I am not now interested in writing total, but I consider that you understood this. If not, just ask me what is your difficulty or doubt. Okay, I hope you got this. Frankly, asking you that, did everyone get this, or you have any problem? Or we can go analogically for getting AF upon FB. So for AF, there comes AC. I can show you here analogically. If we go for AF, we get here AC times sine of angle ACF upon, for FB, we get BC times sine of angle BCF. Okay. And for here CE upon EA, we get that BC times sine of angle CBE over, for EA, we get that AB times sine of angle ABE, and this product is equal to 1. I just substituted the values. Now you observe AC, AC, BC, BC, AB, AB cancel, and hence we are done. That is the trigonometric form, and converse can be proved by using some contradictory ways. No worry about that. Okay. I hope you got this. Hmm? So by using the trigonometric form, we can easily show internal angle bisectors of all three angles of a triangle are concurrent. By using the trigonometric form of Seva's theorem, we can prove this easily. Okay, I just recalled one part. Now, it's a long time that I worked on this, but I am just recalling one part. That's very famous part you must be knowing. Suppose we have a triangle such that none of its angle is 120 degree. Then you must be knowing this theorem. And we draw the equilateral triangles either all inside or all outside. So here we drew the equilateral triangles. Then we know that suppose this is our triangle ABC, okay? And here APC, BQC, and ARB are equilateral triangles drawn in the exterior. Okay. No, it is. I am talking about Fermat's theorem. Then Fermat's point. So what we have? Yes. In interior also it is the same. Yes. The sum is the least. That is not we are entertaining. We can say that here. Then AQ, then PB, and CR are concurrent. This we need to show. And now we would be restricted with the typically our Seva's theorem or trigonometric form of Seva's theorem. We can use that. Only the case is that how to go ahead with that. We are not going to prove it immediately, but I want to show you that. Okay. Now, here my question is that we could draw APC, BQC, ARB equilateral triangles. Now, the question comes, if we have the triangle, say triangle ABC, and if we draw the squares in the exterior, we would be now restricted in the exterior. Okay. So we drew the squares in exterior. Then we are not getting the concurrence if we join some vertices. But if I take the midpoints of such sides, typically these opposite sides, and if we join those midpoints over there, then they are concurrent. We can prove this, or how can we prove this? That's the question. Another question comes, instead of square, if we draw any regular polygon, then what will happen? How we are going to get the concurrences? I hope you are getting it. Another fact is that instead of regular polygon, if I go with some typical, that if this is, suppose I am coming over here, say this is our triangle ABC, then I drew some congruent angles over here. All are equal. In my figure, they don't maybe, but it's okay. Okay, suppose they all are equal. And then now we join these. Then even if they are concurrent, okay, that's typical. So instead of any regular polygon, we go like this. Then even if we get the fact, and moreover, if there is triangle and I draw these equal angles and here these equal angles, can I get the concurrence? So all these configurations can be proved by taking in consideration with our Sehwag's theorem, at least. It can be proved by in many different ways. See how we develop the thoughts. We started with the drawing the equilateral triangles in exterior. We are restricted with exterior. Then we started to draw the square, then the regular pentagon, then the regular hexagon, and so on. Then we try to get such typical concurrences. Then we turn our attention without drawing anything like, because something common as in this figure. But if we change some part, then are they concurrent? So you can keep these problems with you and work. Okay. So I actually worked on these questions some many years back. And then after some years from that point, I went through one book, and in that book, almost the similar kind of developments were given, but in more general than what I thought. So I was really amazed because I didn't think of this part, which was also included in that. Okay, so that is a typical thing that how we get the concurrences. Okay, yes, I think we should go ahead with our part. Hmm. I just gave you for exploratory work like this. Yes. Yes. That's what the thing. But for others, you can play the role because instead of 60, you can take Sharrow any alpha and then you can play. Okay. Instead of 60, alpha is fixed, like because they are regular polygons. So okay, yeah. Let's go ahead. Yeah, let ABC be a triangle. P be its interior point. Let x1, y1, z1 or z1 be the intersections of AP, BP, and CP with BC, CA, and AB respectively. Furthermore, x2, y2 and z2 be the reflections of the points x1, y1, z1. Actually, we need to read it as x sub 1, y sub 1, z sub 1, but it's okay. We read it as x1, y1, z1 or z1 over the midpoints of BC, CA, AB respectively. Then we need to prove that lines AX2, BY2, CZ2 are concurrent. And this point of concurrence is termed as isotomic conjugate of P with respect to WRT with respect to, yes Atharva, with respect to triangle ABC. So that point is termed as isotomic conjugates. And moreover, I can just tell you over here, moreover, 2 points on a side of a triangle are isotomic points. See, isotomic conjugates are different and isotomic points are different. 2 points on a side of a triangle are isotomic points if they are equidistant from the midpoint of the side. Okay. So here in our figure, x1 and x2 are isotomic because of side BC. Similarly, y1, y2 are isotomic points because of side AC, and z1, z2 are isotomic points. Okay. So the condition is that it is not necessary that when I get isotomic points, then always concurrence happen. In some case, suppose for one typical 3 Savians, I get the concurrence. Okay. So I will draw the figure. Oh. Okay. Arey yaar. Now it's okay. Say our triangle ABC. This is our point P. This is x1. This is, arey yaar, I need to change little bit. Just a minute. Sorry for the inconvenience. Y1, Z1. This is our point P. So if such thing is there, then reflection around median. How can we say, Shreyan, like this? Because reflection through a line is different, no? Because median is a line and we are reflecting on the same side from the midpoint. Am I right? Okay. So here we have now the midpoints. Okay. And their reflections. X1 comes over here. Y1 comes over here. And Z1 comes over here. So this is our X2. This is our Y2. This is our Z2. And when we draw them like AX2, BY2. Now in my figure it is not coming, but it's okay. Oh ho 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 ho. Something like this. Okay, let's play a little bit. Oh, I will change the positions. So these are our points. Okay, it's okay. We drew by hand, so it may happen over. So this is the isotomic conjugate of point P with respect to, I mean the point of intersection of the medians. With whom intersection? Intersection happens of median, but with what, Shreya? Yes, sometimes isotomic conjugates help us to solve the problems. Like, for example, Jargon point and Nagel points are the isotomic conjugates of triangle ABC. Am I right? If you try to visualize that. Last time we have seen those points.
Can you just draw them again, sir?
Uh, who said? Who talked? Can you repeat?
Can you draw those figures again?
Okay, you know what is Jargon point and what is Nagel point?
So the Jargon point is the intersection of the CVNs which are created from the intersect in the in circle touch points. I
Uh,
don't know the Nagel point.
and yeah, and Nagel point is for the X circle. Okay. Yeah, Nagel point is for the X circles, and then therefore we can get, see, very simple. I can just show you over here. Just a minute. I hope you got this configuration. Proof, proof is just by Sevas theorem. So proof or converse of Sevas theorem, whatever we may term it as Sevas theorem. If and only if statement comes, then converse and the left side, left to right, right to left. Both things are the in consideration. Okay. So at least while solving, we won't be in that much particularness. Okay. To just save the time. I can just show up over here. Yes. And for Atharva, for equilateral triangle, we come at some typical their overlappingness. See, for a triangle, say its in circle touches over here, whatever it. We know that this length is S minus B, if this is B. Am I right? Don't go with my circle, please. Okay, little bit. Because I have spec and I can't see the nearer things. I need to check my number. Okay. And when we have the X circle, then this length little bit like this, it's okay. Somewhere here, it's okay. This point, they are equidistant from the midpoints, which we can show easily. Because, yes, for that point, we will come at sim median and all. And we need to prove them also. As Jargon and Nagel, we have proved. So that part will come surely. Okay. So we can find out that this length is a typical length. Do you know what is it? This length from here to here is in fact S minus C. And then therefore from here to here is also S minus C, if I am not wrong. Suppose it is the touching point. Okay. So here is S minus B. And from midpoint it is A upon 2. You can show that these two are isotomic points. And then therefore we can say that the Nagel point for X touching and this Jargon point for in touching are nothing but the isotomic conjugates of each other. Okay. So let's have one typical, which is not isotomic, but it goes with something similar over there. And sometimes we get confused that we consider, oh, it is isotomic or what, like that. Hmm? Yes. So lemma saying that those 2 points are isotomic points is very useful in Olympiads. Yeah, we look at those isotomic points when they occur. Now, one such example I would like to take over here. Let ABC be a triangle. Point P is its interior point. Then let X1, Y1, Z1 be the intersections, of AP, BP, and CP with BCCA, AB respectively. Okay. Let the circumcircle of triangle X1, Y1, Z1, X1, Y1, Z1 intersect the sides again, intersect the sides again at sides AB, BC, I forgot, sorry, BC, CA, AB. Again at X2, Y2, Z2 respectively. Then we need to prove that AX2, BY2, CZ2 are concurrent. We need to show them as concurrent. I will draw the figure, but I will draw circle first because we are drawing by hand, no? Say ABC, here is X1, here is Y1, here is Z1. Okay. Oh, I got my mistake. Wait. It is difficult to draw by hand, but it's okay. I will try my level best. Hmm. Now we need to draw the circumcircle of triangle X1, Y1, Z1. It's okay. Little bit. And so here we get X2, here we get Y2, Z2, and here we get Y2. It is clear that X1, X2 are not isotomic points with respect to side BC. Y1, Y2 are also not isotomic points. Similarly, Z1, Z2. But we may join these by hand as we drew figure by hand only. Almost. Okay. So we need to show them concurrent. Okay. So for this, how to prove? Then we need to use some power of a point. First of all, we know that AX1, BY1, CZ1 are concurrent. AX1, BY1, CZ1 are concurrent. Therefore, we have AZ1 over Z1B times BX1 over X1C times CY1 over Y1A is equal to 1. Now, if I want to show that AX2, BY2 and CZ2 be concurrent, then by converse of Seva's theorem, I want the ratio that AZ2 over Z2B times BX2 over X2C times CY2 over Y2A is equal to 1. Okay, so there we need to reach. That is what our form that we need to show. Now, before we go ahead, I must show you one part that if we have a circle and if two chords of the circle intersect inside, say chord AB and chord CD, yes, Sharav, then suppose they intersect at point P, then or two chords of a circle intersect at the exterior, then also we have PA times PB is equal to PC times PD. Actually, each of these products is known as the power of point P. And that power, in short, is also, if the point is exterior, then that power is nothing but the tangent segment, what we draw. Say this is PT, so it comes PT square. Or this can be OP square minus R square, where R is the radius of the circle, or R square minus OP square, depending on the position of P. No, Shara, we call it as the power of point. PA times PB is also termed as power of point. Okay. So actually OP square minus R square is the power of point. We say actually the definition of power of point goes OP square minus R square if P is a point. Then whether that OP square minus R square is positive, then P lies in the exterior. When OP square minus R square is negative, then we say that it lies in interior. And if OP square minus R square is 0, then we say that the point lies on the circumference. But its equivalent, its things are also PA times PB. If we draw a chord intersecting, that is actually the second line through P, which intersects the circle in different points A and B, then PA times PB. If A and B are these A and B points are actually, if I go over here, if I go over here, then they are going to converge and coincide over here. So PA times PB would be PT times PT, and that turns to PT square. Okay. So if we shift that AB like PAB like that, then we get. Okay. So PT square is PA times PB or PC times PD, and that is equal to OP square minus R square. Because PT square is simply OP square minus R square because of the Pythagoras theorem. Yeah, negative positive we can, because R square is greater than OP. No, here, if you have the center over here, you can check for the what we can say. If I draw the diameter through this, we can get the same part with think this is OP, this is R, and say this is XY. So XP is nothing but OP plus R, and YP is OP minus R. Okay. Actually R minus OP, sorry. R minus OP, and then therefore we get that. Okay. Similarly, we can prove for PA times PB also in the same manner. If I want, instead of that, if there is the center, oh, where is it? Here. Here is the center. If I draw join this easily, then I get that this is XY. So it is actually PX times PY is PA times PB. PX is nothing but you can get something with our radius and R. Okay, because OP, this is OP plus R, and Py is OP minus R, which is PA times PB, and then therefore PA times PB is OP square minus R square. If interior, it comes like this. Okay, got the idea? Any question? Okay, now coming to our problem. I think I am taking few minutes more and it is okay for you. Okay, yes, thanks. So by power of point A, I say that, so by power of point, for A, I get AZ1 times AZ2 is equal to AY2 times AY1. You can check. From A, I can show you here or otherwise. Okay, and this one. So AZ1 times AZ2 is equal to AY2 times AY1. Similarly, for B, I get that BZ2 times BZ1 is equal to BX2 times BX1, and there CY1 times CY2 is equal to CX1 times CX2. Yeah. Now equality is symmetric. Now tactfully I can see this AZ1 BX1 CY1. So AZ1 BX1 and CY1 that I want over there. So I take that AZ1 times AZ2, that times BX2 times BX1, that times CY1 times CY2 is equal to, and now there other sides we take, that is AY2 times AY1 times BZ2 times BZ1 times we get here CX1 times CX2. Now we are going to shift this BZ1, then CX1 and AY1 on this side. Okay. And we are going to shift AZ2, BX2, CY2 on that side. When these are coming over the here and there, what we are going to get, I am writing over here. So we get AZ1 upon Z1B or BZ1 times their BX1 upon CX1 times CY1 upon AY1 is equal to, and now that part, this we are shifting, so we get AY2 upon CY2 times BZ1, BZ2 upon AZ2 times CX2 upon BX2, and that product is 1 because this side is 1. Now you critically watch this product in the figure. What is it? AY2 times CY2 and CX2 times X2B times BZ2, upon, I am wrong in reading, AY2 upon Y2C. You can check AY2 upon Y2C, then CX2 upon X2B, BZ2 upon Z2A is equal to 1, and then therefore we are done. So AX2, BY2 and CZ2 are concurrent. Okay. And if you look at this, you can recall 9-point circle. Okay, recall 9-point circle. Say x1, y1, z1 are the midpoints, and the circle passing through the midpoints, meeting the sides again. And that again points are the perpendicular feet of the altitudes. So x2, y2, z2 would be the perpendicular feet of altitudes if x1, y1, z1 are the midpoints. If x1, y1, z1 are midpoints of sides BC, CA, AB respectively, then x2, y2, z2 would be the altitudes of that triangle. I hope you got this. As I consider you know what is a 9-point circle. Okay. Yes, and Sharav is right to say that. So we can use 9-point circle configuration to show that altitudes are concurrent. Or because altitudes are concurrent, then medians are concurrent also can be used. Okay. So I think for today it is sufficient. Let's see next time and we will go ahead. Okay. Yes. So bye bye and thank you.